200 billion stars, 1 trillion planets. Our Milky Way is like a vast city, where crowds of rowdy stars light up our sky as they fight for space. Out to the sprawling industrial zones where new stars are forged, and even further out to historic towns where ancient stars reveal clues to how it all began. Modern cities show off some of the most incredible things humans have ever built, full of lights and amazing structures. But all those lights hide something even more incredible. Turn them off and behold a great city in the sky. This is the Milky Way, our very own galaxy. You can think of it as a city of stars, and it's where we've spent all of human history. Our Sun is just one of the 200 billion stars that make up a vast cosmic city, a city we're only just beginning to know. We're picking up the Earth and traveling across thousands of light years, relocating to distant neighborhoods of the galaxy. The Milky Way stretches so wide, so far, that light from one end takes more than 100,000 years to reach the other. And the truth is, we've only just started to understand where we are and what's around us. But before our trip can begin, we need to know what kind of galaxy we live in. It might sound simple, but it's not, because we can't exactly float above the Milky Way to know the type of galaxy. We're inside it, looking out from the middle of the action. When we look out to study other galaxies in the universe, we see that there are basically 2 types of galaxies. The first type, elliptical galaxies, appear as large balls of stars, and no matter what angle they're viewed from, they always look rounded. From a distance, a spiral galaxy looks something like a frisbee. The key to correctly identifying the Milky Way is written across our night sky. The Milky Way, we believe, is a spiral galaxy, not just based on guesswork, but from what we've measured, mapped, and compared. When you look up at that wide band of stars across the night sky, you're actually seeing part of the disk, seen edge-on from inside it. We're part of a giant disk of stars, but that's just an insider's view. We believe, now of course, we can't fly above the galaxy and take a picture of it. We're stuck inside the disk of the Milky Way. It's a massive, rotating group of stars, gas and dust, all held together by gravity. And our Sun is just one of hundreds of billions. We may not be able to leave the Milky Way, but we can still build a picture of it from right here on Earth. In fact, this image is a picture of our galaxy taken from Earth. It's made from 800 million pixels, contained in over 1,000 individual photographs taken from the darkest places on Earth. The photos have been painstakingly stitched together to create this breathtaking view. But impressive as it is, it's only part of the picture. What astronomers really need is a bird's eye view. So astronomers look outward instead, where other galaxies become our reference points. One of the reference points is Messier 74, also called the Phantom Galaxy. It's over 30 million light-years away Yet telescopes like Hubble can still capture it in incredible detail. Its shape, with long arms wrapping around a bright center, gives astronomers a model for what our own galaxy might look like from the outside. Messier 74 is an example of a galaxy that astronomers think looks a lot like our own galaxy. Using satellites to measure the distance and density of stars in different directions, astronomers reveal the architect plan underlying our star city. At the center of the Milky Way lies a bright, crowded region known as the galactic core. You could think of it as the downtown of our star-filled city. From here, two majestic spiral arms, bright bands of billions of stars, sweep out: the Scutum-Centaurus and the Perseus Arm. Along with them are several smaller arms, forming a loose but graceful spiral pattern that defines the shape of our galaxy. From one end to the other, our galaxy measures a staggering 600,000 trillion miles, which could take light 100,000 years to cross our galaxy. Our solar system, including the Sun and all the planets around it, are located here, in a quiet neighborhood nestled between two spiral arms. Our place in the galaxy is a relatively calm part of space, and it's where we've spent all of human history. But not all regions in the Milky Way are like this. Our surrounding neighborhoods are wildly different. Some regions are wild and chaotic, filled with newborn stars that burn fiercely, or old stars that are nearing the ends of their lives. Others are shrouded in vast clouds of gas and dust, where new stars are just beginning to form. Like any large city, there are dynamic industrial zones, where heat and pressure forge new stars, and others die in violent explosions. And just like an old city, our galaxy also has quiet, ancient neighborhoods that hold clues to how it all began. They act like archives, keeping pieces of its early story. Now we head to one of the most spectacular locations in the Milky Way, a place that holds the clue to how the 200 billion stars of the galaxy were first created. This isn't some far-flung destination. In galactic terms, it's relatively close. But even at the speed of light, over 186,000 miles per second, it would still take us about 1,500 light-years to get there. We arrive at a glowing cloud of gas and dust called the Orion Nebula. It's one of the brightest and best-known regions where new stars are forming. Seen through a telescope, it looks like a deep-colored cloud painted across the sky, but it's far more than that. Inside, new stars are heating up, gathering mass and slowly coming to life. These kinds of clouds are called nebulae. Massive, stretching across dozens of light years, and they act as star factories. Under the pull of gravity, parts of these clouds collapse inward. As they do, the material begins to heat and spin, eventually forming new stars and sometimes planets around them. But this cloud isn't just a work of art. It holds the key to how our Sun and every star in the Milky Way Galaxy came to be. The Orion Nebula is just one example. The Milky Way is filled with regions like this, cloudy zones where raw material gathers and creates something entirely new. From Earth, we see some of these areas as bright patches. Others appear dark, as though stars are missing. In reality, the light is simply blocked by thick dust. In every direction across the galaxy, these places mark the beginning of a star's life. Some will shine for billions of years. Some of those stars are still young. Others have burned for billions of years. But among the hundreds of billions scattered across the sky, a few are remarkably close to us. If we were to draw a circle around our Sun, just a few dozen light-years wide, we'd find a small gathering of stars that form what astronomers call our local stellar neighborhood. Even our local stellar neighborhood is a part of a smaller arm called the Orion Arm, a stretch of stars, gas and dust tucked between two of the Milky Way's larger spiral arms. The Orion Arm contains a wide range of star groupings, including both small and large constellations. These constellations stretch across the sky, each holding hundreds, sometimes thousands, of stars. Apart from the Orion Arm, which is the one we live in, there are 5 other major arms that reach through the galaxy. These are the Norma Arm, Scutum-Centaurus Arm, Sagittarius Arm, Perseus Arm, and the Outer Arm. By galactic standards within the Orion Arm, the area around the Sun is considered to be lightly populated. There are stars here, but they're spaced far apart, and most are dim. Still, within a distance of 15 light-years, astronomers have identified around 50 separate star systems. Some of these are made up of just one star, and some are pairs or groups. When you add them all together, this nearby region includes about 65 stars, all within a small circle in galactic terms. Many of these stars are surrounded by exoplanets, worlds that orbit stars beyond our Sun. Some also have disks of gas and dust, where new planets may still be forming. In order to analyze our local neighborhood, we'll have to map out the vicinity. As we begin moving outward from Earth, we'll pass through dozens of light-years of space. Along the way, we'll visit stars that are located in Orion Arms and are close, quiet, and sometimes barely visible. Having traveled 4.37 light-years away from the Sun, we will reach our first stop, the nearest star system to our Sun, Alpha Centauri. This star system is made up of 3 stars. The 2 largest, Alpha Centauri A and Alpha Centauri B, orbits each other. To the naked eye, they appear as a single point of light, but through a telescope, you will see 2 stars locked in an orbit. And then there is the 3rd star, Proxima Centauri, the closest individual star to our Sun, but the term nearest star system only refers to the entire Alpha Centauri system. Alpha Centauri A and Alpha Centauri B revolve around a shared center of mass, following a slightly stretched or elliptical path. One complete orbit takes around 80 years to finish. The distance between the 2 stars changes over time. At their farthest, they are separated by about 35 astronomical units. That's 35 times the distance between Earth and the Sun. At their closest, they come within 11.2 astronomical units of each other, just a little farther apart than Saturn is from the Sun. The entire Alpha Centauri system lies about 4.36 light-years from our solar system. In the grand scale of the Milky Way, this is extremely close, making it one of the nearest star systems to Earth. The most massive, largest and brightest component in the system is Alpha Centauri A. It's a star very much like our Sun, but just slightly larger and more energetic. This star is part of the same stellar class as the Sun, a main sequence star, but with about 108% more mass and a radius of 1.2 times that of the Sun. Even though Alpha Centauri A has a surface temperature and classification similar to our Sun, it gives off about 1.5 times more energy. So far, astronomers haven't confirmed any planets around it. But in 2021, while observing the star in infrared, researchers picked up signs that something might be there. A possible planet-like object. Based on early findings, this object could have a mass between 9 and 35 times that of Earth, and a radius ranging from 3.3 to 7 times Earth's size. It appears to be orbiting Alpha Centauri A at a distance of about 1.1 astronomical units, roughly the same distance as Earth is from the Sun. If it is real, it would take about 1 year to complete a full orbit. This possible planet still needs confirmation. Additional observations are needed to verify the data, which can be done with the help of either the James Webb Space Telescope or Earth-based observatories. Now, let's turn our attention to the second star in the Alpha Centauri system, Alpha Centauri B, also known as Toliman. Like its larger sibling, Toliman is a main sequence star, which means it shines by fusing hydrogen into helium at its core, just like our own Sun. Alpha Centauri B has about 90% the mass of the Sun, and its radius is around 86% of our Sun's. Its surface temperature is reportedly around 5,260 Kelvin, or just under 5,000 degrees Celsius. These numbers may seem close, but they give the star a different character. Because it's cooler, it shines with a soft orange glow, rather than the yellow-white light we're familiar with from the Sun. On average, it is also only half as bright as the Sun. Interestingly, Alpha Centauri B emits a lot more energy in the X-ray range compared with other objects of its class. Powerful flares and ejections are sometimes seen erupting from its surface, bursts of energy that can briefly outshine the rest of the star's light. So far, no confirmed exoplanets have been found orbiting Alpha Centauri B. But back in 2012, a team of astronomers from the Geneva Observatory thought they might have spotted something unusual. After 4 years of tracking slight changes in the star's movement, they suggested there could be a planet very close to it, orbiting once every 12 days, with a radius just slightly smaller than Earth's. This suggestion by the observatory was based on 4 years of observations of the star's motion. However, 3 years later, a mathematical error was discovered in the data processing, and the idea of a planet was dismissed. Now we come to the third and smallest member of the Alpha Centauri system, Proxima Centauri, and it is unlike its brighter companions in almost every way. It is a red dwarf, a small star with a mass approximately 12% that of the Sun. It's a much smaller object too, about 7 times smaller in size. Its surface temperature is just over 3,000 Kelvin, which makes it much cooler than our Sun. As a result, its glow is incredibly dim, and its luminosity is just 0.17% that of the Sun. That's less than 1/5 of 1%. Yet, for all its modest light, Proxima holds a special distinction. It is, in fact, the closest known star to our Sun, lying just 4.25 light-years away. That's why it was named Proxima, from Latin meaning the nearest, and it's not standing still. It is slowly getting closer to us. Astronomers estimate that in around 26,700 years, it will be just over 3 light-years away from our Sun. Even so, you can't see it in the night sky. Its dim light is far too faint to be seen with the naked eye. Proxima is also physically distant from its companions, Alpha Centauri A and B. At present, it sits around 13,000 astronomical units away. That's roughly 0.21 light-years. But over the next 300,000 years, its orbit will bring it a little closer, down to around 4,100 astronomical units, or 0.06 light-years. Its journey is slow and sweeping. Proxima takes roughly 547,000 years to complete a single orbit around the shared center of mass of the Alpha Centauri system. Unlike the larger stars in its stellar family, Proxima Centauri, a faint red dwarf, hosts a planetary system that's surprisingly rich. So far, astronomers have confirmed the existence of 2 exoplanets, with evidence hinting at a possible third, still unverified. And that's not all. Observations in infrared light have revealed what appears to be a ring of dust circling the star, along with the possibility of countless small rocky bodies, like asteroids or comets, quietly drifting through the darkness. The first confirmed planet is Proxima Centauri b. It was discovered back in 2016 using the radial velocity method, a technique that tracks the slight wobbles in a star's movement caused by the gravitational pull of an orbiting planet. Then in 2020, astronomers confirmed this discovery with a closer look, using the powerful instruments of the Very Large Telescope in Chile. The data showed something extraordinary. It showed that Proxima b is extremely close to its star, just 0.05 astronomical units away. For comparison, that's only 1/20th the distance between the Earth and the Sun. At such close range, Proxima b completes a full orbit around its star in just 11 Earth days. 1 year there lasts less than 2 weeks here on Earth. Based on current estimates, this planet is slightly larger and heavier than Earth. Its mass is thought to be between 10 and 20% greater than that of our planet, while its radius measures approximately 1.3 times that of Earth. These numbers place Proxima b firmly in the category of rocky terrestrial planets, a type that we know well. Although Proxima b orbits its star at a distance far closer than Earth does to the Sun, only about 0.05 astronomical units, the star it circles is far cooler and dimmer than our own. As a result, the planet receives only about 2/3 the energy that Earth receives. In other words, it gets 1.5 times less energy than we do. This gentle level of warmth means its average surface temperature hovers around 234 Kelvin. That's minus 39 degrees Celsius. Under the right conditions, liquid water could theoretically exist on parts of the planet, especially if there's an atmosphere thick enough to trap and distribute heat. However, Proxima b is likely tidally locked. This means that one side of the planet always faces its star. On the bright side, temperatures could rise. On the dark side, they remain in perpetual icy weather. If Proxima b does have a dense atmosphere, it could help balance this divide, moving heat from the sunlit side to the dark one. Earth's own winds and oceans do something similar every day. But Proxima Centauri, the planet's parent star, is not a quiet companion. As a red dwarf, it is known for frequent and violent stellar flares. These bursts of high-energy radiation could strip away any fragile atmosphere over time. Without a strong magnetic field to protect it, Proxima b would be left vulnerable. Even so, chances of such a field existing are slim. In 2020, another planet was confirmed in the system, Proxima Centauri c. This planet lies roughly 1.5 astronomical units from the star, with an orbital cycle slightly over 5 years. At such a distance from a faint red dwarf star, sunlight is barely a whisper. The planet completes one full orbit in 5 Earth years, moving slowly through the cold outer edge of this miniature planetary system. Based on current estimates, Proxima c's mass is 6 to 8 times greater than Earth's, though its radius is still unknown. That puts it into a super-Earth or a mini-Neptune. We don't yet know its radius, so we can't say for sure what kind of world it truly is. It may have a thick gaseous envelope like Neptune, or a solid rocky surface wrapped in ice. What we do know is that Proxima c is frigid. Its surface temperature is thought to be just 39 Kelvin, which is about 234 degrees Celsius. At those temperatures, almost nothing can remain liquid, not even the gases we take for granted here on Earth. Even so, some observations suggest that Proxima c may host a ring system, one that is 5 times wider than Jupiter's. If true, this would be an extraordinary feature, an immense halo of ice and dust encircling a frozen world. And Proxima c might not be alone. According to the latest data from the Very Large Telescope, there could be yet another exoplanet nestled even closer to the star than Proxima b. This hypothetical world would lie just 0.029 astronomical units from Proxima Centauri. That's closer than Mercury is to the Sun. It's thought to be very small, only about 25% the mass of Earth. But even at that size, it would be a world of extremes. At that proximity to its star, it would complete an entire year, a full orbit in just 5 Earth days. Its estimated surface temperature would be around 360 Kelvin, or about 87 degrees Celsius. Hot enough to boil water, but still potentially within a range where atmospheres could exist. Depending on its structure, whether this planet really exists or whether it was a measurement error remains uncertain. For over 100 years, the Alpha Centauri system, our closest stellar neighbor, has been quietly listening to our radio waves sent from the Earth. Ever since the earliest broadcasts in the early 20th century, our signals have been traveling through space at the speed of light, slowly reaching the stars. Today, they've passed Alpha Centauri, but the vastness of space remains a formidable challenge. This star system lies over 40 trillion kilometers from Earth. Even light, the fastest thing in the universe, needs more than 4 years to make that journey, while our fastest spacecraft would take tens of thousands of years to arrive. However, advanced technologies could theoretically reduce this time. Since the dawn of space exploration, many projects have been proposed for interstellar travel, but none have been built. Most were abandoned. But one project is still under active consideration: the Breakthrough Starshot program. Instead of large spacecraft, this idea uses tiny probes, no bigger than a computer chip, with ultra-thin sails. Powerful lasers from Earth would push them to 20% the speed of light. At that speed, they could reach Alpha Centauri in just 20 to 25 years. Though still in the early stages of development, Breakthrough Starshot represents humanity's first realistic step toward interstellar travel. Having traveled 6 light-years away from the Sun, we will reach our second stop, a small red dwarf designated GJ 699, also known as Barnard's star. It is remarkable to think that it shines too faintly to be seen with the naked eye. And yet, Barnard's star holds a unique distinction. It moves faster across our sky than any other star we know. Over the span of just 180 years, it will noticeably change its place against the background of the stars. To give a sense of just how fast that is, if you tracked its motion over time, it would appear to move across the same patch of sky where the Moon travels. Not in front of the Moon, of course, but along the same stretch of sky that the Moon regularly crosses in its monthly orbit. This red dwarf is slightly moving towards the solar system at a speed of slightly over 100 kilometers per second, and is going to become our closest star in about 10,000 years. At that time, the distance between us and Barnard's star will shrink to just 3.8 light-years, even closer than the Alpha Centauri system. And yet, despite being so close by, this star will still be nearly invisible to the naked eye. This kind of movement, called proper motion, is exceptionally rare to witness in a single human lifetime. But Barnard's star shows us that the sky is not as still as it seems. Barnard's star may seem quiet and distant now, but it is not standing still. This small red dwarf is steadily heading in our direction, on a slow but determined path toward our solar system. That's because Barnard's star, like other red dwarfs, doesn't shine very brightly. It gives off only a small fraction of the light our Sun does. The star's mass is just 17% that of the Sun, and its radius is 6 times smaller than that of our Sun. Its surface temperature is around 3,134 Kelvin, which is just under 2,900 degrees Celsius. And because of its small size and lower temperature, the star gives off very little light. In fact, its brightness is 2,300 times less than that of our Sun. If you were to live near Barnard's star, our Sun would appear in the night sky with a magnitude of about plus 1.4. It would look like a modestly bright star, similar to Regulus or slightly dimmer than Spica. This makes Barnard's star incredibly hard to detect without telescopes, even though it's so close to us. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. They had been tracking its subtle motion against the backdrop of more distant stars. What they found was a faint but consistent wobble. That invisible wobble led to the discovery of what may be a planet, an exoplanet orbiting close to this quiet red dwarf. Named GJ699b, it is believed to be a cold super-Earth, a rocky world with a mass at least 3.2 times that of Earth. This planet orbits its star at a distance of about 0.4 astronomical units. That's roughly 40% the distance from Earth to the Sun. At that range, it takes 233 Earth days to complete one full orbit. Because Barnard's star is a cool red dwarf, GJ699b receives far less warmth and light than Earth does. Sadly, the position of this planet, GJ699b, makes it difficult to study directly. From our perspective here on Earth, it doesn't pass in front of Barnard's star. That means we can't observe it using the spectral methods often used to detect atmospheres or surface compositions. All thanks to mathematical modeling, we can begin to form a picture of what this planet might be like. In fact, the planet orbiting it receives about 50 times less energy than Earth receives from the Sun. As a result, the temperature on its surface is frigid, around 105 Kelvin, which is minus 168 degrees Celsius. Although GJ699b is frozen on the surface, scientists don't rule out the possibility that something warmer could be hiding below. If tidal forces caused by the gravitational pull between the planet and its star, or radioactive decay within its core, are releasing enough energy, they might be heating the planet's interior. That warmth could create a subsurface ocean, sealed beneath thick layers of ice. And if such an ocean exists, it might have been there for billions of years. Here, in the quiet southern skies of the constellation Vela, lies a mysterious pair of celestial bodies, two brown dwarfs locked together, spinning through space. Their names are Luhman 16a and Luhman 16b. Together they form what we call Luhman 16, discovered only in 2013. This binary system is the third closest system to our Sun, just after Alpha Centauri and Barnard's star. And yet, unlike blazing suns or glowing giants, these objects do not shine brightly. Brown dwarfs are sometimes called failed stars. They are born the same way stars are, from collapsing clouds of gas and dust. But they never gather enough mass to ignite full hydrogen fusion in their cores. As a result, they glow dimly, not from the fire of sustained fusion, but from the fading heat of their formation. Luhman 16a and 16b orbit one another at a distance of about 3.5 astronomical units, roughly the same as the gap between the Sun and the asteroid belt. One full orbit takes 20 Earth years, a slow and gentle ballet played out in deep space. Their temperatures hover between 1,300 and 1,600 Kelvin, just above the heat of molten rock, hot enough to glow faintly in infrared, yet far too cool to illuminate the night sky like true stars. And still, they are not dead. Brown dwarfs are known to host active atmospheres filled with silicate clouds, metallic rains, and powerful winds. In fact, Luhman 16b became the first brown dwarf ever to have its atmospheric weather patterns mapped. Observations using the Very Large Telescope in Chile captured rolling planet-sized storms and rapidly shifting cloud structures. demonstrating that even in the absence of sunlight, dynamic processes shape these strange worlds. Imagine a sky with no sun, no stars. Just a dim red haze and stormy clouds above a dark horizon. That is the world of Luhman 16. While no exoplanets have yet been confirmed around Luhman 16, this system continues to spark curiosity. In 2013, astronomers reported possible hints of a planetary companion, a body that may have been influencing the subtle motion of Luhman 16b. Some suggested this object could be a planet with several times the mass of Earth, orbiting close to one of the brown dwarfs. The signals weren't strong enough to confirm it, and follow-up studies have yielded mixed results, but the possibility remains. If a planet were to orbit here, it would exist in perpetual twilight, its skies illuminated not by a blazing sun, but by two dim, flickering brown dwarfs. There would be no daylight, at least not in any way we are familiar with. That's because brown dwarfs never gained enough mass to ignite sustained hydrogen fusion in their cores, the process that makes stars like our Sun shine brightly. Instead, they glow faintly in the infrared part of the spectrum, giving off a dull or reddish warmth. So if a planet were to orbit this pair of brown dwarfs, its skies would never see the bright blue of daylight. Such a world would likely be extremely cold. Temperatures might hover just above absolute zero, the point at which all molecular motion stops. But that doesn't mean the planet would be lifeless. And if the gravitational forces from the two brown dwarfs created tidal heating beneath its surface, like we see on Jupiter's moon Europa, pockets of heat could form deep underground life. Having now travelled nearly 8 light years from the Sun, we arrive at our next destination, a quiet red dwarf known as Wolf 359. It is far too dim to be seen with the naked eye, shining with less than 1/10,000th of the Sun's brightness. And yet, this tiny star is one of our closest neighbours in the galaxy. Wolf 359 lies within the constellation Leo, and like many red dwarfs, it keeps a low profile. Its mass is only about 9% of the Sun's, and its radius is less than 16% that of our star. This gives it a much cooler surface temperature, around 2,800 Kelvin, or just over 2,500 degrees Celsius. It glows with a faint red light, casting no warmth into space, no brilliant shine. But like so many of the stars around us, Wolf 359 is not still. It is in motion, part of the endless ballet of stars orbiting through our galaxy. It moves through space at a quiet pace and slowly changes position with time. Though it may never come as close as Barnard's star or Alpha Centauri, its proximity reminds us that our Sun does not sit alone in the dark, and that even in the quietest corners of space, there are neighbours to be found. Wolf 359, like most red dwarfs, is not a strong source of light. In fact, it gives off only a very small amount of energy compared to our Sun, so little that it remains invisible to the naked eye, even though it's one of our closest neighbours in space. Now imagine standing on a planet near Wolf 359. If you looked up at the night sky, our Sun wouldn't appear large or brilliant as it does from Earth. Instead, it would shine with a modest brightness, a small point of light among many, no more dazzling than a typical first magnitude star. As for planets, no confirmed worlds have been found orbiting Wolf 359 yet, but astronomers have searched and continue to search for signs of distant companions, small wobbles in the star's motion, or dimming in its light that might suggest a planet passing in front of it. If a planet does exist there, it would be deeply cold, receiving only a fraction of the warmth that Earth gets from the Sun. It would lie beneath a sky cast in permanent twilight, lit only by the pale red glow of its parent star. Even so, this quiet little star is part of the story of one of our neighbors in the galaxy. It may not burn brightly, but its nearness makes it a key point on the ever-growing map of stars that surround us. Meanwhile, on the other side of the Sun lies the almost exact opposite of the dim red dwarf. The star we're talking about is Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. To the casual observer on Earth, Sirius appears as a single dazzling point of light, the brightest star we can see in the night sky. But in reality, it is not a single star. Rather, it's a two-star system. The brightest star we can see in the night sky. But in reality, it is not a single star. Rather, it's a two-star system. This system, located in the constellation Canis Major, consists of a pair of stars orbiting each other, Sirius A and Sirius B. At this moment in their long orbit, the two stars are separated by about 30 astronomical units. That's roughly the same distance between our Sun and Neptune. They're currently as far apart as they can be, slowly circling a shared center of gravity. The larger and brighter of the two is Sirius A. This massive blue-white star holds twice the mass of the Sun and is about 70% larger in diameter. Its surface is searingly hot, reaching a temperature of 10,000 Kelvin. This intense heat gives Sirius A the power to emit 25 times more energy than our own Sun. Its brilliant light is what makes Sirius shine so vividly in our night sky, even from nearly 9 light-years away. On the other hand, Sirius B is a much smaller and quieter companion. It is a white dwarf, a dense, compact remnant of a once larger star. Though it's only about 12,000 kilometers in diameter, roughly the size of Earth, it has nearly the same mass as the Sun packed into that tiny space. This incredible density is due to the way white dwarfs are formed. When a star like the Sun reaches the end of its life, it can no longer produce energy through fusion. Its outer layers are pushed away into space, leaving behind only the hot, heavy core. With no outward force to balance the pull of gravity, the core collapses inward until it is stopped by a strange type of pressure known as electron degeneracy pressure. The result is a star that is no longer powered by fusion, but still holds the full weight of a Sun, packed into a space no larger than Earth. Its surface is astonishingly hot, reaching temperatures of around 25,000 Kelvin. That's more than twice as hot as Sirius A, but despite this heat, it gives off very little light, making it nearly impossible to see without a powerful telescope. In fact, Sirius B is about 1,000 times dimmer than its larger companion. After years of searching, astronomers have found no signs of exoplanets orbiting either star. One possible reason is the system's relatively young age, just a few 100 million years. Another explanation is that the angle of the system's orbit prevents any planets from passing directly between the star and Earth, which is how many exoplanets are discovered. Some scientists believe that Sirius B once lived a very different life, roughly 120 million years ago, before it became a white dwarf. It is thought to have expanded into a red giant. During that time, it would have shed its outer layers violently, flooding the system with intense radiation and stellar winds. That dramatic phase may have destroyed any planets that were forming or had already formed, ripping apart the disk of gas and dust that once circled the young stars. Today, Sirius A and Sirius B continue to orbit each other slowly. It takes them 50 years to complete one full revolution. Over the next 60,000 years, Sirius will inch ever closer to Earth. At its nearest point, it will lie just 7.5 light-years away, closer than it is today and even brighter in our skies. But that brilliance will not last forever. Sirius A is still in the prime of its life, but it too will eventually run out of fuel. In about 660 million years, it will begin the same transformation its companion already underwent, expanding into a red giant, then collapsing into a white dwarf. For a brief moment, Sirius A will flare with extraordinary brightness. Its light will flood the skies, shining thousands of times more powerfully than before. Within months, the flare will fade, and slowly Sirius A will grow dim, joining its companion, Sirius B, in silence. The brightest star in our sky will disappear, its place taken by the quiet glow of two fading remnants. After leaving the area around Sirius, a region filled with powerful ultraviolet light and intense stellar winds, our next destination is a small, quiet star located 14 light-years from Earth. This star is known by different names in various star catalogues, but one of them, and popular name, is Wolf 1061. Wolf 1061 is a red dwarf, a type of small, cool star that glows dimly in space. It has only 30% the radius of the Sun, and its mass is about 4 times smaller than that of our star. The surface temperature of Wolf 1061 is around 3,272 Kelvin. Because of its small size and cooler temperature, it gives off very little light. In fact, its total brightness is only 0.14% of the Sun's, which makes it invisible from Earth without a telescope. Despite its dim characteristics, Wolf 1061 hosts one of the most interesting planetary systems found in our nearby galactic neighborhood. Astronomers have discovered 3 exoplanets around it, rocky worlds that are similar in composition to Earth, but each with very different environments. The closest planet to the star is called Wolf 1061b, which orbits the host star just 0.038 astronomical units away. That's less than 4% of the distance between Earth and the Sun. Because of how close it is, this planet completes a full orbit in only 5 days. Wolf 1061b is thought to have a mass between 1.5 and 2 times that of Earth, and a radius about 20% larger. It likely shows the same face to the star at all times, a condition known as tidal locking, meaning one side always stays hot in constant daylight, while the other remains in perpetual darkness. Because it's so close to its star, Wolf 1061b is blasted by intense heat and powerful stellar flares. The high-energy radiation and fast-moving particles make it unlikely that this planet has any atmosphere left. Without protection, its surface would be scorched on one side and frozen on the other. Scientists have found that these harsh conditions make Wolf 1061b extremely difficult for life to form. The second planet in the Wolf 1061 system is called Wolf 1061c. It orbits a little farther from its red dwarf star, about 0.089 astronomical units away. At that distance, it takes the planet only 18 days to go all the way around its star. What makes this world especially interesting is that it sits in the habitable zone of its host star. A habitable zone means the region around a star where temperatures might allow liquid water to exist on the surface. That doesn't guarantee life, of course. But it does make Wolf 1061CE one of the more promising nearby planets. This world is larger and heavier than Earth. Its mass is estimated to be 3 to 4 times greater than Earth's, and its radius is about 1.6 times larger. This puts it in the category of super-Earth, rocky planets that are bigger than our own, but not as massive as gas giants like Neptune. Because of its size, the surface gravity on Wolf 1061c would also be stronger than Earth's. Scientists believe it would be about 60% higher, which means you'd feel noticeably heavier standing there. Wolf 1061c receives less heat and light from its star than Earth gets from the Sun. Its average temperature, called the equilibrium temperature, is about 223 Kelvin, or minus 50 degrees Celsius. That's still warmer than Mars, but far too cold for Earth-like conditions on the surface unless something else helps keep it warm. And here's where things get more hopeful. If this planet has a thick atmosphere, especially one with greenhouse gases, it could trap enough heat to raise surface temperatures. That would allow for more stable climates and even the presence of liquid water in some regions. Seasonal changes, weather patterns, and even day-to-night shifts could also play a role in shaping the environment. If these conditions are just right, Wolf 1061c might not be a frozen wasteland after all, but a cold, rocky world with patches of potential. Of all the planets we've found so far that might support life, Wolf 1061c is one of the closest to Earth. In fact, it ranks 5th on the list of potentially habitable exoplanets nearby our galaxy. The third planet in the Wolf 1061 system is known as Wolf 1061d. Unlike its siblings, this world moves in a highly stretched out orbit, what astronomers call an eccentric orbit. At its closest approach, the planet comes within 0.21 astronomical units of its red dwarf star. But at its farthest point, it moves out to 0.73 astronomical units. That's quite a wide range, and because of this, the planet experiences big changes in the amount of energy it receives during its journey around the star. It takes about 217 Earth days for Wolf 1061d to complete one full orbit. That's just under 8 months on our calendar. In terms of size and mass, this planet is much larger than Earth. It has about 7.7 times the mass of our planet. What it actually looks like, though, depends on its structure. If it's a rocky planet, similar in composition to Earth, Its radius would be about 1.7 times larger. But if it's more like a mini Neptune, a planet with thick layers of gas and possibly a deep atmosphere, then its diameter could be at least 2.2 times greater than Earth's. Despite its size and orbit, Wolf 1061d never crosses into the star's habitable zone. That means it likely remains too cold or too unstable to support life as we know it. Its unusual orbit and size make it a fascinating example of how planets can develop under very different conditions. The Wolf 1061 system, with its 3 rocky planets, has become one of the most studied nearby systems in our Milky Way Galaxy. And as our instruments improve, new discoveries will likely be made here in the near future. In addition to hosting a fascinating planetary system, Wolf 1061 stands out for its position in space. This star lies at the edge of a far larger structure called the local interstellar cloud. This cloud is not like a fog or dust storm we might imagine. It's an immense region stretched over 30 light-years across space, filled with extremely thin, hot hydrogen gas. The hydrogen gas is also incredibly hot, with temperatures reaching around 7,000 Kelvin. Despite its vast size, it's almost empty. On average, there's only about 0.3 of an atom per cubic centimeter, far less than a single full atom in that tiny space. This is about half the average density of interstellar matter in the Milky Way. Even this nearly invisible cloud plays a part in our understanding of space. It's part of a much larger neighborhood known as the local bubble, which itself is located within one of the spiral arms of our Milky Way Galaxy, the Orion Arm. This is the same galactic arm where our Sun resides, along with most of the nearby stars we've visited on our journey through the Milky Way. For the past 10,000 years, our solar system has been quietly gliding through a vast and nearly invisible region of space, known as the local interstellar cloud. Right now, our solar system is nearing the edge of this cloud. We've been inside it for millennia, but we won't remain here forever. In fact, astronomers estimate that we will exit the local interstellar cloud in about 2,000 years. After that, we'll enter a new region of space, one that is even thinner and hotter, a place where the density of gas is even lower and its temperature even higher. Nearby stars are already in different parts of this vast galactic web. For example, Alpha Centauri, our closest stellar neighbor, is no longer in the same cloud. It now resides in what's known as the G cloud, another thin region of gas and plasma drifting through this part of the galaxy. The edge of the local interstellar cloud is not just an abstract boundary. As we cross into a new region, the heliosphere, the bubble of solar wind that surrounds and protects our solar system, may begin to behave differently. Interactions between solar wind and interstellar gas can influence how cosmic rays reach Earth. These subtle changes might even have long-term effects on our planet's space weather, or perhaps on the climate itself. Even though space appears empty, it's not the same everywhere. The solar system doesn't sit still. It moves through these invisible regions, each with its own story. So, in the great scale of time and distance, we are always passing through, always entering a new part of the galaxy. And while the stars may appear still from Earth, everything around us, including us, is in constant motion. But what does the local interstellar cloud really do? It's a kind of cosmic weather system, a place with a very specific density, temperature, and magnetic behavior. It affects how the solar wind behaves. It changes the shape and size of the heliosphere, the giant bubble created by the Sun that protects Earth from high-energy particles. And it helps astronomers understand how stars, like our Sun, move through space and interact with the galaxy. The local interstellar cloud is believed to have formed when two massive bubbles of superheated gas collided in the distant past. These bubbles were created by powerful explosions, supernovae, that occurred nearby in our galaxy millions of years ago. The leftover gas from those explosions compressed and shaped the cloud we now move through. It also inherited motion, drifting through the galaxy at an angle to the solar system's path. This motion isn't random. It's carried by the larger structure of the local bubble, a giant cavity in the galaxy's interstellar medium, like a hollow in the clouds carved by ancient stars. And all of this floats within our galaxy's Orion Arm, the same spiral arm where the Sun and most nearby stars are located. But the cloud isn't just made of gas. It also carries its own magnetic field, and it gives off a soft background radiation that adds to the invisible energy of space. Despite how energetic and hot the particles in the cloud may be, there's no danger to life on Earth. That's because we're well protected. The solar wind, a constant stream of charged particles flowing from the Sun, forms a kind of shield around the solar system called the heliosphere. This barrier deflects much of the incoming interstellar gas. And for anything that does make it past that outer shield, Earth still has one more line of defense: its atmosphere. Thick and protective, our air absorbs most of the remaining high-energy particles, keeping life on the surface safe and untouched. If we stop and look around for a while, we will find that we have already traveled more than 30 light-years away from our solar system. But even farther away, within this region of space, there are over 1,000 stars, most of them single, some in pairs and others in groups. The most striking example is Castor, a complex system with as many as 6 stars. This star system is about 50 light-years away from Earth. When we look up at the night sky, it appears as a single point of light and can be seen without a telescope. It's one of the brightest stars in the constellation Gemini, second only to Pollux, and is also the 23rd brightest star in the entire night sky. People have known about Castor since ancient times because of how bright and easy it is to spot. The two main stars in the system are called Castor A and Castor B. They are bright bluish-white stars, similar in appearance to Sirius. Each of them has a smaller companion star nearby, which is a red dwarf. These two pairs form two separate star systems, but they don't just sit still. They orbit around a shared center of mass. The distance between these two binary pairs is about 110 times the distance from the Earth to the Sun. As a result, full orbit between them takes about 445 years to complete. About 600 times the distance between the Earth and the Sun away from Castor A and B. There's another pair of stars, but these two are much smaller and cooler. They are both red dwarfs, and they are almost identical to each other. Each of these stars has about 60% of the Sun's mass, and their surface temperatures are around 3,900 Kelvin, which is cooler than most bright stars. These two red dwarfs are very close together, so close in fact that they orbit each other in less than 20 hours. That's a full orbit in less than a single Earth day. Together, this tight-knit pair orbits around the entire Castor system in a very stretched-out elliptical path. It takes them about 14,000 years to make just one full trip around the system's center of mass. So far, astronomers haven't found any confirmed planets in the Castor star system. But that doesn't mean there aren't any. If there are planets in this system, they're most likely to be orbiting the faintest stars, where the environment might be a bit calmer. In 2018, scientists noticed something interesting. They were studying Castor C, one of the dimmer stars in the system, and they detected tiny changes in its orbit. These changes may suggest that another object may be tugging at it with gravity. That hidden object is likely a brown dwarf, something more massive than a planet, but not massive enough to shine like a star. Based on their calculations, this brown dwarf is about 49 times more massive than Jupiter. It orbits Castor C at a distance of about 14 astronomical units. It's also quite possible that Castor C, like many red dwarfs, may host rocky planets. If such worlds exist, the view from their surface would be nothing short of breathtaking. Imagine standing on such a planet. In one part of the sky, you'd see two deep red stars slowly circling one another, casting a soft, warm glow. In the opposite direction, the sky would never fully go dark. Instead, it would remain in a state of eternal twilight, brightly lit by two powerful stars, each hundreds of times brighter than the Moon appears from Earth. But for now, this vision remains just that, a possibility. No one has yet confirmed whether these planets exist. The mystery continues to inspire astronomers searching for signs of distant worlds. Even though the stars we've visited are spread far apart, they all belong to the same giant structure in space. This region is called the local bubble, and it stretches about 300 light-years across. Inside this bubble, there are thousands of stars, including our Sun, and several interesting features, like the local interstellar cloud we passed through earlier. The local bubble is part of our galactic neighborhood, a wide, mostly empty space shaped by ancient cosmic events. Around 10 to 15 million years ago, several massive stars in this part of the galaxy came to the end of their lives. When they ran out of fuel, they exploded as supernovae, powerful blasts that sent shockwaves throughout the space. These powerful explosions sent shockwaves through space, blowing away the nearby gas and dust. Over time, they cleared out a huge empty space in our part of the galaxy, like a giant bubble carved out of the material that usually fills the space between stars. Inside the local bubble, alongside the local interstellar cloud, the one our solar system is currently traveling through, there are other nearby clouds of gas. Two of the most notable are the G cloud and the apex cloud. These clouds are also made of hot, low-density hydrogen gas, much like the one we're passing through. They float quietly inside the bubble, slowly drifting through space. The solar system is actually very close to the edges of these clouds, and in the future we may pass from one into the other. Even though these clouds are incredibly thin, far thinner than anything we experience on Earth, they still help scientists understand the space between the stars. Studying them tells us how the environment around our solar system changes as we move through the galaxy. The local bubble isn't alone in space. It's surrounded by other similar bubbles, giant empty areas shaped by ancient explosions. The center of Bubble 1 is about 500 light-years away from us, and even though space is vast, the solar system is slowly heading in that direction. In several tens of millions of years, we'll begin to reach the outer edge of this neighboring bubble. Clouds of superheated gas, groups of young stars, huge glowing nebulae, and long streams of stars. These are the beautiful building blocks of our Milky Way Galaxy. The Milky Way Galaxy doesn't stand alone. They join together to form even bigger shapes, like long threads and walls made of stars, stretching across billions of light years. Here and there, brilliant flashes of light come from some of the most violent and dangerous neighborhoods in the entire Milky Way. Here, stars aren't born, they die. This is where we begin to approach one of the Milky Way's major spiral arms, and closest to the Orion Arm, the Scutum-Centaurus Arm. Unlike the Orion Arm, which is just a small spur tucked between the bigger arms of the galaxy, the Scutum-Centaurus Arm is one of the Milky Way's true giants. It wraps halfway around the galaxy, stretching across tens of thousands of light-years, starting near the galactic center and sweeping outward like a glowing ribbon of stars and gas. This region is bursting with activity, such that huge clouds of gas and dust swirl together under gravity's pull. Shockwaves from long-dead stars ripple through the arm, squeezing this gas tighter and tighter until new stars begin to ignite. Here, stars are born in massive clusters, some of them hundreds of times the mass of our Sun. But they don't live long. Massive stars like these burn through their fuel quickly, and when they die, they go out with a bang. Exploding as supernovae that send waves of energy sweeping across the galaxy. Some of the largest stellar nurseries in the Milky Way lie in this arm. One of the most famous is Westerlund 1, a young star cluster packed with giant stars and exotic objects like magnetars. Neutron stars with magnetic fields billions of times stronger than Earth's. Even so, the Scutum-Centaurus is called the Red Supergiant Factory. That's because it contains some of the rarest stars in our galaxy. Massive red supergiants that are nearing the ends of their lives. These stars are enormous, bloated with age and glowing in deep shades of red and orange. They're incredibly bright, but also unstable, preparing for a final dramatic ending. RSGC-2 in particular hosts around 26 red supergiants, extremely rare and massive stars nearing the end of their lives. Even more impressive, RSGC-2 is the largest known group of red supergiants in our entire galaxy. Stephenson 218, the largest star ever discovered by radius, also resides here. It is believed to have a staggering size of about 2,150 times the radius of the Sun. Significantly larger than stars like SCUTI, which we will discuss later. It lies about 19,000 light-years from Earth and is, by all current measurements, the largest known star by radius in the entire galaxy. If placed at the center of our solar system, its surface would extend well past the orbit of Saturn. And yet, despite its enormous size, this red supergiant is relatively cool on the surface, about 3,200 Kelvin, or roughly 2,900 degrees Celsius. Its deep red hue glows softly across the vast clouds of dust and gas that surround it. This behemoth is part of a massive stellar cluster, Stephenson 2 or RSGC2, home to dozens of other red supergiants, a rare and mysterious collection of stars nearing the ends of their lives. Other than its size compared to the Sun, it is also incredibly bright, over 600,000 times brighter than the Sun. However, it doesn't shine in visible light like our Sun. Instead, it glows mostly in infrared, hidden behind a thick layer of dust and gas. This dusty shell blocks much of its visible light and makes it hard to study. That same dust suggests the star is shedding its outer layers at a rapid pace, losing mass faster than most stars we know. Its temperature is relatively cool for a star, around 3,200 degrees Kelvin. That gives it a deep red glow. But this reading is so low that some astronomers question whether it's even accurate. Some believe the thick dust around the star is skewing our measurements. The same goes for its position and movement. Its velocity through space is slightly different from the other stars in Stephenson 2, making scientists unsure if it's truly part of the group. Astronomers estimate that this massive star is losing material at a very high rate, about 1.35 times 10 to the minus 5 times the mass of our Sun every year. That might not sound like much, but for a single star, it's an enormous amount. This kind of intense mass loss suggests that Stephenson 2-18 is nearing the end of its life, and could have recently experienced a powerful event where it shed a large amount of its outer layers. Despite all the questions, one thing is clear. Stephenson 2-18 is a dying giant. It's nearing the final stage of its life, and sooner or later it will explode in a powerful supernova. We know this because of the strong infrared glow surrounding the star, heat energy coming from dust and gas that the star has ejected into space. Scientists have also detected masers around it. These are naturally occurring radio signals, kind of like space lasers, produced in the thick clouds of gas around certain kinds of stars. Both Stephenson 2-18 and another star in the same cluster, D2, emit these masers, which is a strong sign they're losing mass very rapidly. The explosion will send newly formed elements into space, which might someday help form new stars and planets. What's more, Stephenson 2-18 gives off strong signals from silicate dust, especially at infrared wavelengths like 10 and 18 microns. Water masers, radio signals from water molecules, have also been detected, further confirming how active and unstable this star has become. All of this tells us we're watching a dying giant in its final turbulent phase, shaping the space around it as it prepares for a spectacular end. Beyond Stephenson 218, this cluster holds 25 other red supergiants, an astonishing number considering how rarely such stars appear elsewhere in the galaxy. In most regions, these types of stars are rarely found, but here they gather together in one extraordinary stellar family. Some of these stars are still relatively stable, massive, bloated, and glowing a deep red. For example, Stephenson 2D2, Stephenson 2DFK 49, and more. These red supergiants began life as bright, blue-white stars, burning hot and fast. But over millions of years, they grew enormous, their outer layers swelling until they reached hundreds, sometimes over 1,000 times the diameter of our Sun. Despite their age on cosmic timescales, often just 10 to 20 million years old, they've already entered the final stages of life. Over time, their cores fused heavier elements, while their outer layers expanded dramatically. Some have grown to over 1,000 times the diameter of our Sun. Their once blue light has shifted to a deep crimson glow, signaling that these ancient titans are nearing their inevitable end. When a red supergiant reaches the end of its life, things get dramatic. Deep inside, its core collapses under its own gravity, and in just a moment, the outer layers of the star are thrown into space at incredible speed. This is what we call a supernova, one of the most powerful explosions in the universe. What's left behind depends on how massive the star was. Some collapse into neutron stars, tiny ultra-dense objects. They mix with clouds of gas and dust, helping form the next generation of stars and planets. This region shows us what happens to massive stars near the end of their life. Found near the center of the Scutum constellation, close to dense star-forming regions, SCUTI is a red giant located in the constellation Scutum. The constellation Scutum is the original host of Stephenson 2 and more. By current estimates, SCUTI is around 1,700 times the radius of our Sun, making it the second largest known star by size, just behind Stephenson 2-18. To put that into perspective, if SCUTI were placed at the center of our solar system, its outer layers would reach somewhere between the orbit of Jupiter and Saturn. It would completely engulf Mercury, Venus, Earth, Mars, and even Jupiter. The scale is simply mind-bending. Despite its gigantic size, SCUTI is relatively cool on the surface, about 3,365 Kelvin, which is cooler than the Sun. This gives the star its distinctive deep red hue, characteristic of red supergiants. SCUTI shines with a luminosity nearly 340,000 times greater than the Sun, though like Stephenson 2-18, most of its energy is not in visible light. Instead, it glows primarily in the infrared, hidden behind clouds of gas and dust that makes it difficult to observe with ordinary telescopes. SCUTI was first discovered in the mid-19th century, but it wasn't until the 2010s that astronomers realized just how large it truly was. Then, in 2012, using the Very Large Telescope in Chile, astronomers observed SCUTI and two other red supergiants. Of the three, SCUTI stood out as the biggest and brightest. It lies about 9,500 light-years from Earth, much closer than Stephenson 218, and that proximity has helped scientists study it in greater detail. Original estimates placed it about 9,500 light-years away, but newer data from the Gaia spacecraft suggests it might be closer, around 5,900 light-years. If that's true, the star would be smaller and dimmer than once thought. Only around 755 to 900 times the Sun's radius and 124,000 to 340,000 times as luminous. SCUTI has no known companion star, which makes it harder to determine its exact mass. But based on models of stellar evolution, it's estimated to be somewhere between 7 and 10 times the mass of our Sun. Similar to that of Stephenson 2-18 SCUTI is a dying star, a red supergiant in the final phase of its life. Like others of its kind, it began life as a hot, massive blue star, burning through its fuel at a furious pace. But over millions of years, it expanded outward, becoming unstable and swollen. Right now, it's shedding mass at a significant rate, losing its outer layers through powerful stellar winds. This process creates a shell of dust and gas around the star, obscuring much of its visible light and helping to cool it down even further. Eventually, it will collapse under its own gravity, triggering a supernova explosion that could outshine its entire galaxy for weeks. Here and there, brilliant flashes of light come from some of the most violent and dangerous neighborhoods in the entire Milky Way. Here, stars aren't born, they die. We journey from the familiar neighborhood of the Sun to the wonders of the Perseus Arm, nearly 6,500 light-years away. Here lies one of the galaxy's most beautiful sights, the Crab Nebula. The Crab may look static, but gases are racing out from its center at over 3 million miles an hour. It was put into motion by a phenomenally powerful and violent event in the past. When we look at the gases of the Crab Nebula spreading out into space and trace their movement backward, we discover they all came from the same spot about 1,000 years ago. Although it's made of gas and dust, this nebula hasn't created stars yet. This area represents the industrial zone of our galaxy, where the building blocks of Earth were manufactured long ago. The Crab Nebula is a fascinating object with very rapidly expanding gases. Back on Earth, 1,000 years ago, early civilizations watched the heavens. In 1054, Chinese manuscripts described the sudden arrival of a brilliant new star. It shines brighter than any other star, so brightly it was visible during the day. But then it mysteriously disappeared. Today, the Crab Nebula lies in exactly the same part of the sky, where the Chinese observed their brilliant star. What they witnessed was the moment the crab was born. The Crab Nebula was produced by the colossal, titanic explosion of a star at the end of its life. It's a supernova remnant. The spiral arms of our Milky Way are littered with these colorful remnants, tombstones of stars that died violently in cataclysmic explosions called supernovas. To figure out this mystery, astronomers need to locate the next victim, a massive star at the brink of death. It takes supernova light 1,000,000 or even 1,000,000,000 years to reach its death period. Astronomers deduce that only stars with a huge mass go out with a bang. A massive star has a very vigorous life. Initially, it fuses hydrogen to form helium, producing the energy that makes the star shine. Then, the ashes of that reaction, the helium, fuse together to form carbon and oxygen, releasing yet more energy. The carbon and oxygen can fuse into still heavier elements: magnesium, sodium, neon, then silicon and sulfur, and finally iron. When it starts to make iron, the giant star is doomed. In the core, a fierce battle takes place. Energy pushes outward, holding the star up, while gravity tries to crush it inward. The battle continues as the star makes heavier and heavier elements, producing energy while fending off total collapse. But once it starts to form iron, the battle is lost. Fusion of iron nuclei into heavier elements does not release energy. It absorbs it. An iron core builds up until it becomes so massive that gravity wins. The iron core collapses in less than a second. The outer layers collapse inward, then rebound and get blown to smithereens. But from this death comes new life. All the iron in our world was created and ejected into the cosmos by gigantic stars that exploded as supernovae. Those explosions created the iron, spread it into space, and it was later incorporated into planetary systems like ours. Ultimately, the atoms of iron were forged in the hearts of exploding stars. Supernovas are the industrial zones of our star city, cosmic foundries that forge new elements. In catastrophic explosions, heavy elements are thrown into our galaxy, enriching it over billions of years. Without these stellar industrial zones, we wouldn't have the raw materials here on Earth. It's all linked. We are all linked to the cosmos. Our lives today are only possible because of events that happened billions of years ago in the hearts of supernovas. Even the heavy elements in our bodies, the carbon in our cells, the calcium in our bones, the oxygen we breathe, and the iron in our blood, all were created through nuclear reactions inside stars and ejected into the cosmos by supernovae. But only a handful of stars are massive enough to die as supernovas. Most stars, like our Sun, end their lives more gently. A typical star will die with a whimper, not a bang. Death comes when the gravity pulling in finally overcomes the nuclear energy pushing out. When this happens, any star, even our Sun, will die. In about 4 or 5 billion years, it will grow into a much bigger star called a red giant. At that time, the Sun's outer atmosphere will be held so loosely that the gases will drift away into space, in what might be called a cosmic burp. These cosmic burps leave behind dying stars that litter the spiral arms as they slowly shed layers of elements. Some layers are oxygen, some are silicon, and some are sulfur. These are the different colors we see in Hubble Space Telescope images. Not far from our Sun is a place where a star is dying, the Helix Nebula. It shows us how most stars end their lives. Our Sun is destined to follow a similar path when it dies. 5 billion years from now, the Helix Nebula lies about 650 light-years away in the constellation Aquarius. It was created when a star, similar in size to our Sun, reached the end of its life. As it ran out of fuel, the star shed its outer layers into space. What's left behind is a glowing cloud of gas and dust, shaped like a giant eye, one reason it's nicknamed the Eye of God. At the heart of the nebula is the star's hot core, now a white dwarf. It's about the size of Earth, but with almost the same mass as the Sun. This tiny leftover emits intense radiation that makes the surrounding gas fluoresce, lighting it up in stunning blues, reds and greens. The Helix Nebula spans about 2.5 light-years across, making it one of the closest and largest planetary nebulae visible from Earth. Despite being close, it's still faint and requires a telescope to see clearly. What we see from Earth is actually a 3D structure viewed from the side. The full nebula is shaped more like a smoke ring or prolate sphere, a stretched-out bubble tilted slightly in our direction. One of the things about Helix Nebula is the presence of comet-like knots, dense clumps of gas with long tails. There are around 40,000 of these knots scattered across the nebula. Each one is roughly the size of our solar system. These knots are shaped by radiation from the white dwarf and are slowly dissolving into space. The gas in the Helix Nebula is still expanding, moving away from the central star at speeds up to 40 kilometers per second. This process began over 10,000 years ago, and the whole nebula might only shine for another few thousand years before fading away. The central star of the Helix Nebula is a white dwarf with a surface temperature of 120,000 Kelvin, hot enough to emit powerful ultraviolet rays. Some scientists believe it may even be surrounded by a dusty ring formed from ancient comet-like objects. There's also evidence suggesting it might be eating a former planet, possibly the remains of a gas giant that once orbited too close. But in other neighborhoods of the galaxy, stars suffer a fate worse than death. At the center of the galaxy lies a place where stars disappear altogether. We're taking the Earth from the safety of home to the heart of the Milky Way. It's a dynamic, exciting district, but also a risky place to be. As we head downtown, the number of stars increases, and the density of stars is tremendous at the center of the galaxy. If we were to take a trip from the spiral arms out, where we are by the Sun down to the center of the galaxy, it would be an interesting trip. It would be very much like moving from the suburbs into the heart of a very busy metropolitan area. As we head downtown, the number of stars increases, so the density of stars becomes tremendous. At the center of the galaxy, it's about 1 billion times higher than out here by the Sun. Here at the center of the galaxy, there are so many stars in the sky that the Earth is bathed in perpetual light. It's a stunning but dangerous sight to behold. The stars aren't just close together, they're moving at super speed. Going to the heart of the galaxy might not be dissimilar to going to an amusement park. The rides are somewhat similar to how the stars orbit the center of the galaxy. So something has to be going on at the center of our galaxy that lets every star move at super speed. But figuring out what is no small task. The heart of our galaxy lies 26,000 light-years away. It's difficult to observe through the vast amounts of stars, gas and dust. And there's another problem even closer to home, the Earth's atmosphere. The atmosphere is great for us. It allows us to survive here on Earth. But it is an absolute headache for astronomers. Imagine trying to spot a pebble at the bottom of a moving stream. The ripples distort everything you see, That's exactly what the atmosphere does to starlight, especially when we try to look deep into the crowded, dusty center of our galaxy. So, astronomers use a technique called adaptive optics to get a better view. By measuring how a laser beam is distorted in moving air, it's possible to compensate for the atmosphere's blurring effect. The stars that astronomers want to see are the ones at the very center. Without adaptive optics, this region looks completely blurry. You can't see the individual stars. If we zoom into the very heart of the galaxy, we can see the data collected over the last 15 years. You can see the stars and the tremendous motion they've gone through. In particular, S2 star. S2 moves much more quickly as it gets to the center of the frame, showing something unusual happening in that region. Putting together all the measurements, astronomers have been able to make an animation showing how the stars have moved over the course of 15 years. For an object to have enough gravitational pull to send S2 on such a rapid orbit, it must have a huge mass. S2 completes one orbit every 15 years, and from this, astronomers know there are 4 million times the mass of the Sun confined within its path. There is only one known contender that has a giant mass but is so small: a black hole. And so, the center of our galaxy lies a massive black hole, an object whose gravity is so strong that not even light can escape it. This is a real image of the center of our galaxy. We can't see the black hole, but we can see bright clouds of dust and gas spiraling toward it. We're nearing the black hole. It's at the center of a stream of dust and gas, the debris of stars blown apart after straying too close. Black holes grow over time, and that happens by material falling into it. And that material can come in the form of either gas or stars that gets torn apart. One of the stellar nursery regions we're about to visit is truly stunning. What makes it so beautiful is the mix of bright and dark areas stretching across the flat disk of the galaxy. Perhaps the most beautiful part of this image is that we have this contrast of dark and light regions running through the plane of the disk. What that really is dust. Clouds of dust that are casting a shadow from the back of the star. The stars are trying to shine their light through, but there are dust clouds blocking the light, much like a cloud on Earth would block the sun. These vast clouds of cosmic gas and dust stretch thousands of light years across the Milky Way. Hubble finds them in most spiral galaxies. Dark, ghostly bands woven through the spiral arms and spreading across the entire disk. But there's something strange about this gas and dust, as sometimes it glows. These bright, glowing clouds are called nebulas. Each one is unique and breathtakingly beautiful. The Eagle Nebula has towering pillars up to 4 light-years in size. These immense columns, some up to 4 light-years in height, are so large that our entire solar system could disappear within them many times over. Its most famous feature is the Pillars of Creation, towering columns of dense gas and dust photographed by the Hubble Space Telescope. Farther south in the sky lies the Carina Nebula, a nursery of glowing gas and turbulent energy. The Carina Nebula has its distinctive green glow. These vibrant colors reveal what gases nebulas are made of. For example, if there's oxygen gas, you get a green glow. If there's hydrogen gas, you get a red glow. analyzing the light from a nebula is very instructive. It tells us what's there, what the physical conditions are, how dense it is, how hot it is, and what it's made of. An infrared camera, for example, can detect the heat coming from a hot cloud of dust. This is just like a star hidden inside a cloud of gas and dust that infrared astronomers can detect using an infrared telescope. In a visible light picture of the Orion Nebula, we see all the gas in front of what we know are stars in the background. But in an infrared image, we can pick out the stars inside the nebula and see dusty cocoons around them. Even though the Orion Nebula is located in the Orion Arm of our galaxy, scientists use it to learn about how new stars are born. But scientists still need a way to strip away the remaining dust. The way to do that is with an X-ray picture. When we transition into the X-ray image, we can see just the stars themselves. The X-rays coming from the surfaces of the stars, allowing us to study them in great detail. By analyzing the light from these stars, astronomers make an astounding discovery. Hidden within the Orion Nebula are some of the youngest stars ever found, just a few 100,000 years old, a mere heartbeat in the life of the galaxy. And it's not just the Orion Nebula. Nebula's house baby stars in every spiral arm of the galaxy. These regions are nurseries for new stars. There are young stars heating up the surrounding gas clouds and making them glow pink. Stars are made of gas, and our galaxy has plenty of it. In fact, you can think of our galaxy as having an atmosphere of gas and dust surrounding all the stars in the disk. It is from this gas that new stars are born. It all starts inside a cold, dark cloud of dust and hydrogen gas where a quiet tug-of-war begins. The cloud wants to dissipate like smoke in the air, but gravity wants to pull it together. In a balance between gravity pulling in and gas pressure pushing back out. Gravity wins and the material crunches down into a disk, the beginning of a star. As gravity pulls more gas toward the center of the disk, it gets denser and hotter until finally, at 18 million degrees, a miraculous transformation takes place. Hydrogen atoms fuse together to form helium. With a burst of nuclear energy, a star begins to shine. These stars eventually get their nuclear fires going in the core, heating up and expelling the material around them, clearing up the neighborhood. Over the next few million years, winds blow the surrounding gas into spectacular swirling patterns, revealing the place where the star was born. A human lifetime is too short to witness a star's birth in real time. But by speeding up millions of years of cosmic evolution into a few seconds, we can see one star born after another. Both nebulae remind us that the universe is a place of constant creation. Clouds collapse into stars. Stars ignite and shine. And one day, they too will end their lives in brilliant explosions, scattering new ingredients for the cycle to begin again. These nebulae are not just clouds. They are the birthplaces of stars. Stars are born from gas and dust. They shine for millions of years and eventually return their materials to space through dramatic explosions. This ongoing cycle of creation and destruction is what fills our galaxy with wonder. Nowhere is this more vividly on display than in one of the Milky Way's most dramatic landscapes, the Scutum-Centaurus Arm. It is here that we find colossal star clusters, rare supergiant stars, and brilliant stellar nurseries. regions bursting with life and energy on a cosmic scale. We leave our solar system and rise out of the spiral arms of the Milky Way. Up ahead lie vast clusters of stars that orbit the heart of our star city. There are over 150 of them. These satellite towns, called globular clusters, hold the answer to one of astronomy's greatest mysteries, the true age of our galaxy. Globular clusters are fascinating. They contain about 1 million stars each, packed tightly together. If you could visit one, the night sky would be spectacular, with many stars shining as brightly as the full moon. The sky would be filled with bright nearby stars. It'd be like fireworks all the time. Besides the sheer number of stars, there's something even more intriguing about these clusters. One of the very interesting aspects of globular clusters is there's no sign of young stars. Stars are like people. You can look at them and guess their age and the lives they've led. With people, grey hairs and wrinkles are the telltale signs. With stars, it's their colour and size. By measuring the brightness and colour of stars in a globular cluster, we can figure out how old they are. And here's the remarkable thing. They're very old. In many cases, the stars in globular clusters of the Milky Way are almost as old as the universe itself. Globular clusters are living fossils. They're like discovering a community of people who've been around since the Stone Age. Some stars here have been shining for 12 billion years, more than twice as long as the Sun. And that's a helpful tool for estimating the Milky Way's age. Globular clusters are part of our galaxy. They orbit it, acting like tracers for its history. Because they're so old, they tell us the galaxy itself is also one of the oldest objects. And our galaxy isn't just old, it's very old. In fact, the Milky Way is one of the oldest objects in the cosmos. It's been around almost since the beginning of the entire universe, at least 12 billion years. Globular clusters also show that the chemistry of the galaxy back then was very different from how it is today. We can measure the chemical makeup of those stars, and it turns out they have very little of the heavy elements.